Okay, so hi everyone. It's a pleasure today to have Professor Venkatesh Saligrama from Boston University speaking to us. He got his PhD at MIT, and in general he's been working on the areas of signal processing, statistical learning, video analysis, and generally information decision kind of systems theory. And he has been the recipient of several awards, including the PKF Award, as well as the ONR Young Investigator Award, the NSF Career Award, and so on. So please welcome Professor Venkatesh Saligrama.
Thank you. Thank you. So today I'll be talking about Shannon information theory and sparse recovery. The idea is to try to come up with a connection between Shannon information theory, as in the noisy channel coding theorem, and lots of these different kinds of things that are popular these days called compressed sensing and so on and so forth. Okay. This is joint work with my student Chem Aksoilar and my former student George Attia, who is now a assistant professor at University of Central Florida. Okay. So here is a brief outline for my talk. First of all, we will simply talk about the noisy channel coding theorem and then the sparse recovery problem, and try to connect them, try to explore how these two are connected. Then we'll look at a large number of examples. I'll try to convince you that lots of different types of examples that you might be familiar with fall into these classes of problems that we can call it as sparse recovery. Then we will try to formulate the problem of sample complexity, which is essentially what we want to learn in sparse recovery problems, meaning how many samples are required to recover the sparsity pattern in many different settings. And then I will then give theoretical results for different types of cases: high dimensional case, independent identically distributed case, non-independent identically distributed case, and so on. And then we'll come back and apply these results to several applications and give concrete bounds for these different applications. And then if I have some time, I will also try to extend some of these ideas to what is called as the value of information that is popular in some of the Muri topics that we have seen. Professor Kumar will be familiar with this. So that's what we are going to talk about. Okay. So what is the noisy channel coding theorem at a very high level? I have a finite set of messages. Each message is encoded into a coded signal of length t that passes through a noisy channel, produces a waveform, noisy waveform. Let's call it the observed output yt. T here denotes the signal length, and then the decoder tries to decode the message that was sent. So that's the thing that Shannon in 1948 set up to analyze. Now, why is this very important for us? Because the noisy channel coding theorem, one aspect of it is that it maps messages to waveforms of length t. The main implication of the noisy channel coding theorem for us is that it provides bounds for the maximum number of distinguishable signals. So here is a result which is quite well known. 1/t times the log of the number of messages is smaller than the mutual information. If the mutual information is bigger than 1/t times the log of number of messages, then one can show that, at least asymptotically, one can decode this message, which message was sent. Another way of writing the same expression is in terms of the probability of error. Minus the log of the probability of error in decoding can be expressed as being proportional to the mutual information minus the rate at which messages are sent. And another way of writing this, which we will often use in this talk, is that the log of the number of messages divided by the mutual information between the coded signal and y. If it is smaller than t, then indeed you can make sure that the probability of error goes to 0. So please keep in mind this particular expression, which says that the log of the number of messages divided by the mutual information, if that is bounded from above by the number of samples t, or the length of the signal t, then you can decode the message that was sent. Of course, there are lots of different assumptions here that I'm not going to get into. I just want to sort of keep this at this point at a high level. So what does this have to do with sparse recovery problem? Okay, so let's try to formulate the idea of sparse recovery. So in my perspective, we have a random vector. Let's call them features or covariates or anything that you would like to call it. There are d different features. I numbered them x1, x2, x3 up to xd. And then I have observations. These observations are target variables y. Here is the sparse model that we want to think about. This is the fundamental assumption for the entire talk. The assumption is that if indeed we believe in sparsity, then it means that there is a subset S of features, which is, this has to be actually D, not N, because there are D features. There is a subset S contained in 1, 2 up to D, such that the probability of the likelihood of Y conditioned on the subset of the features, X of S, is exactly equal to the probability of Y conditioned on all the different features. So the probability of Y conditioned on x1, x2, x3 up to xd is exactly equal to the probability of Y conditioned on the subset of features x1, x2, x sub S, where S is some subset of this index set from 1 through n. You can also write this in a convenient form as a Markov chain where you have xs complement, where this is the complement of S in 1 through D. X of S and Y forms a Markov chain, which means that the middle guy is independent. The middle guy, when you conditioned on the middle guy, the stuff here and there are independent conditioned on this middle guy. Please stop me if I'm confusing anybody anywhere. Okay.
Sure.
Okay. So now that is your sparse model. The point is you do not know S, right? You do not know S. There is some subset of features that are relevant. That's what this condition means. The subset of features that are relevant, if I know that subset of features, conditioning on those features completely decouples the problem, in the sense that the probability of Y conditioned on that subset makes it completely independent of other features. And the task is to figure out which subset S is relevant. So you are allowed to collect T data samples. I call them X superscript I and Y superscript I. And then you can collect them into a block length XT and YT. And you want to figure out, the goal of our problem is to figure out S from data. So you do not know S. All you know is that if there is some S which is relevant and satisfies this Markovianity equation, and the goal is using T samples to determine which subset S is the correct subset. Okay? Okay, so why does this have to do with information theory or noisy channel coding theorem? Well, as you can see, the way I've set up the problem, you can think of that relevant subset or the support of relevant subset or the support of the signal as S, and S lives in a discrete space. There are only log of, again, this shouldn't be N, this has to be D, I apologize. There are log of D choose S different bits. You can think of that as a message. Nature, in our view, in signal processing problems, nature codes this into the signal of length T. If you exactly know this S, you exactly know what that code is, which is X sub S of T, and then it goes through a channel, produces an observation. Okay, In channel coding, you are allowed to completely design this coded signal to be anything that you want. So I'm optimizing over all these coded signals so that I can do the best job I can to recover the message. In signal processing, I do not have control over this coder in almost all interesting cases. In fact, even if I have some flexibility, I have a lot of constraints on what can be coded, what can be the allowable maps from S to excess of T. Okay, that is a fundamental issue that will come up again and again. So in this sense, you can view our problem, which is sparse recovery problem, in this block scenario where the input consists of the subset that you do not know, and it's a discrete subset. There are only discrete number of messages and discrete number of different bits that are going to be input, which you do not know. We know this for every single possible message. You know the mapping, and then you have a channel output which you know as well. So the goal is to figure out which subset is correct given the observed output and how the coding function works. So let's try to understand this through a whole bunch of examples so that we don't get lost in what I'm saying right now. So let's consider the idea of non-adaptive group testing, a subject that maybe many of you may know, but I will just repeat this so people can understand. This group testing actually started somewhere in the World War II, where they wanted to test soldiers to figure out who had a specific disease. So in this context, imagine that you have S soldiers in a large population having a disease. I keep saying N, but N is really D, if I were to use my notation from before. So there are 12 soldiers here. 3, 6, 10, and 12 are the people who have a disease. What the idea in group testing was that you would pool the blood samples from different groups of these people. For instance, you will construct pool 1. Pool 1 would pool the blood samples from person 1, person 2, person 4, and person 7. Pool 2 will pool blood samples from 1, 2, 3, 4, and then pool 3 would pool resources from 7, 8, 9, and 11. So once you do that, you test the pooled blood samples. Here is for this pool, there is nobody in this pool who has a disease, so this will be a positive test. Somebody in this pool has a disease, so this will be a negative test. Specifically, 3 has a disease, so this will be a negative test. And in this pool again, I guess, yeah, nobody has a disease, so it has to be a positive test. So how does this? You can also think of this, if you don't like group testing, you can also think about this problem, exactly the group testing problem, in the context of fault localization in all optical networks. So you send out a probe, and you have a network, and then some of the links in the network are bad. You send out a probe through this network. If every link in this network is good, then you will get a positive test. On the other hand, if some link in this pool is bad, meaning along this path is bad, then you get a negative test, which means one of the links along this path has a bad link. So how can you form? So that exactly is a group testing problem, because for your tests or your pools are all paths, and each path is going to be either labeled positive or negative based on whether or not that particular path contains a bad link or a good link. Now, how can you formulate this as a non-adaptive group testing problem, as a Shannon theoretic, information theoretic problem? First of all, notice that you have different patients. which is going back to 2 slides earlier, you have different patients, and each one of these rows correspond to columns. So the first column pools the blood samples from the first person and the 5th person and so on. Second pools blood samples from the 3rd person and so on. And a test is negative if the pool does not contain the bad apples. In this case, the people who have the disease are the 2nd person and the 3rd person. So here you see in the 2nd column, 2nd row, the 3rd person has been pooled, and therefore the test is positive. Right? So anybody any pool that has any of these 2 people will be positive. Now, the main point is this matrix and these tests satisfy Markovianity, which I was telling you about, because the probability of these observations conditioned on all the items here, all the people here, is equal to the probability of y conditioned only on these 2 columns. So the probability conditioned on all the columns is exactly equal to the probability of these tests conditioned on only this subset of columns. So therefore, you can formulate this problem as a Shannon theoretic problem where the message is the set of items that are defective or have disease, which is 2 and 3 here, and then that gets mapped to a code, which are these 2 columns here, and that goes through some kind of a Boolean channel, and maybe it is noisy. You may get false alarms and so on, and we'll study some of these things later, and you produce an output y. Okay. The main thing I want to point out here is that even in this very simple case, we cannot design this code to be arbitrary in the sense of the original thing that Shannon was looking at. That is because Shannon's design would have been for any 2 different messages that are different, the corresponding codes are going to be independent of each other. However, because 2 subsets here could overlap, for instance, you could have 2, 3 or 2, 4, and the intersection will contain 2, the corresponding signal that is produced do overlap, and therefore you cannot rely on the fact that you can code them independently. So different messages cannot be coded independently. So that's a fundamental constraint that we have to live with, that we cannot simply take Shannon's theory and apply it here because of this reason. Okay. So this is a congested IP linked clause problem. I'll skip this because it's the exact same problem as the one I described with the fault with this fault localization in all optical networks. So I'll just carry on. Carry on here. Now, this is yet another problem, which is compressive sensing. Maybe a lot of you are familiar with it. Again, this problem could also be looked at in the way that in the Shannon theoretic sense, and that's because imagine what is a compressed sensing problem. You have real valued observations. There is some matrix X which consists of random variables which multiply this column vector, and this column vector contains sparse set of coefficients. So the green, red, and the blue, those are only the 3 coefficients that are non-zero. All the whites are 0. You do not know which are non-zero. You only know and which are 0 basically. And the goal is to figure out not only these coefficients but also the amplitudes of those coefficients. However, this problem still, even in the noisy case, as long as the noise is independent, satisfies this Markovianity issue, which is the probability of the observations y conditioned on the set of all columns is exactly equal to the probability of y conditioned on the subset of columns where you have non-zero items. So if I condition on the columns corresponding to 4, 6, and 13, then the probability of this likelihood of y conditioned on that is exactly equal to this. So how does this work in our sense, in our framework? You would put 4, 6, and 13 here. The waveform that I call here maps it to those per specific set of columns. These are columns drawn from the 4th column, 6th column, and 13th column, and the channel produces an output y. Now you may ask, where does the amplitude at 4, amplitude at 6, and amplitude at 13 go into? And they'll go into the channel. And we'll come back to this point. Why do I put this back in the channel a little later? But that's basically how this gets mapped. Okay. So you can extend this idea to anything that you want. There I had a linear model. You don't have to have a linear model. You can completely deal with a nonlinear model. And the nonlinear model would be something like this. Supposing I quantized x times beta plus w, something that happens in single pixel camera, then you have this block diagram for how this happens. Beta gets multiplied by xs, noise gets added and quantized. But we want to rethink how this block diagram works in our context. S is the subset where the support of beta exists, and that gets coded into x of s. And then the channel takes care of the non-zero values of beta and the noise and the quantization effects. All the nonlinear effects, the amplitude of beta in the non-zero part and the noise all go into the channel, and leaving behind only a discrete quantity here that we want to estimate. Okay. Here is another example, wireless channel estimation. What is wireless channel estimation? You have an observation y, that is, and you have an input x. The channel itself has some impulse response denoted by these non-zero coefficients beta k. These corresponds to the different multipath reflections, and that serves as an impulse response. That is the reason why you have a convolution here. X gets convolved with the non-zero coefficient beta, and the noise gets added. How can you think about this? In our context, the support of the impulse response serves as your message. The code itself is the columns of the input of the corresponding Toeplitz matrix that corresponds to the delays, the multipath delays, and the inputs, the reflections that you get corresponding to those delays would be here. And the channel absorbs all the channel coefficients, the value of the channel coefficients, not the support, just the value of the channel coefficients, producing an observation y. So basically this is like a Toeplitz matrix, and still you would have probability of yt given xt equals the probability of yt given xs. So like this, you can almost formulate a large class of problems in this way. You can even formulate a Markov random field type idea in this context, because what is a Markov random field? It is the probability that what you observe at these nodes conditioned on its neighborhood is independent of all the rest of the world. And that's exactly sort of what is our Markovianity assumption is stating. Okay? I hope if I've confused anybody, please ask me some questions. So I just want to summarize what we have learned so far. So for linear models, what are the two things that are unknown? The support of beta is unknown, and the value on the support is unknown. The way we deal with this problem is to put the support out here and the values out here. And the reason why we want to do this is because we want to absorb all the discrete components of what you do not know, like finite set of messages, into the thing that you want to estimate, and we want to think of the value itself as a nuisance that we really don't want to deal with. Our goal is to simply figure out the support first, rather than somehow fuzzify the problem and make it more complicated by combining this quantity and that quantity and estimate them jointly. So our goal is not to estimate them jointly, and that is the main difference between what we are trying to do here versus a lot of the related work that has gone on, where you come up with estimation algorithms that try to estimate both the support and the value of the support. What we are trying to do here is not to estimate the value, we just want to estimate the support. And the reason we want to do this is because the set of all supports, the number of different possibilities, is only discrete and finite, and we can write a clean information theoretic problem and analyze this in a clean manner. Now you may ask, how can I find the beta, right? The point is, estimating beta in many cases itself is quite easy if you know the support. It's actually a straightforward least squares regression problem. So if you knew the support, then you can just condition this onto the support and just solve a least squares problem. And lots of bounds exist, and that really doesn't cause a problem. And that's another reason why we do not want to try to think about the value of the support, but only the support. You can do exactly the same thing for nonlinear models. Again, in nonlinear models, we assume some kind of a prior distribution on beta exists, and again, there's a support set S and a value on the support, and the value of the support is absorbed into the channel, and only the support goes into the code. Okay? So you can estimate the value after you've estimated the support. Now, let me summarize what we have learned so far. We have a Shannon style noisy channel coding block diagram. You have some discrete object S, which is the set of all possible supports for your signal processing problem, and that gets coded, produces an XS, goes into a noisy channel, produces a Y. Now the main difference between channel coding and our problem is that we have limited control over the coder, and so we have to deal with constraints on the coded signal across different message sets. And
a question?
Yeah.
So if there is no coding involved, why is it different from estimation?
If there is no coding involved, it is not different from estimation. It is similar to estimation.
So okay. So one question I'm thinking is the code book problem somewhat similar to choosing what bases to choose? Is that the connection? Is that close? Does that make it closer to channel coding? Because you can have different bases, right? And bases, yeah. So even though you don't have very detailed choice of the code words available, you could still choose the bases. The basis, sorry, the basis.
Yeah. So there are. So the way I want to respond to this point is that you could have completely no choice of X of S, which means X of S is completely given to you in certain cases, and in certain other cases there may be some choice in XS. For instance, in some problems in group testing, you can choose X of S, what items you pull. In certain other problems, such as wireless channel estimation, you have much less control because you have the Stokes structure and so on and so forth. So there it is closer to an estimation problem, except that it's a sparse estimation problem, but it's really not sparse estimation because I'm not going to estimate the coefficients. I'm only going to estimate the support of those coefficients. So it is an estimation problem, but I'm going to estimate only the support of those coefficients. Does that make sense?
All right.
Okay.
Yeah.
Yeah. So the difference between the estimation and the problem here is simply that I'm going to pull out the value, the real valued amplitudes of the coefficients and throw them into the channel as nuisance parameters, and I'm only going to keep the support or what non-zero coefficients exist, whether they are 0 or non-zero, and throw them out here into what I call as a code, or what I call as a message. And there is a map from that message set to the to the observations. Some set of observations are these x's, and some set of observations are the actual observations y. Okay, so it is very close to an estimation problem, but actually I'm only interested in the discrete part of the estimation problem. I'm not interested in the continuous aspects of the estimation problem. That's basically the difference. Okay, so why did we do this? Because it allows us to state very simple theorems that exactly tell you how much information is required, how much data is required to figure out S, that discrete object S. So let's get into some kind of technical details. Problem formulation, I'm just repeating what we have already discussed. There's some ground truth, which is S is some subset of 1 through D. We assume that it's uniform. We don't know anything about it. It could be any possible support of size S. We are going to assume that S, X, and Y are all random variables. And the objective, which is I'll just do a max likelihood estimate of the support based on my observations collected up to time t, x, t, y, t. You can formulate a number of different error expressions. The probability of error, point-wise probability of error for a fixed S is probability over x and y such that the max likelihood estimate is not equal to S conditioned on S. You can also formulate a total probability of error where you take the average over all possible S as well. Then you can also formulate expressions such that what is the probability that the distance, the Hamming distance between the support that you estimated and the true support is equal to some number L, and you can call this P, E, L. And for all of this situations, you can ask what is the sample complexity? What does sample complexity mean? You want to understand what is the minimum value of T such that as you scale D and S, that's the number of different features, and the support S, the probability of error is guaranteed to go to 0. So we want lower bounds and upper bounds for this. What is the best possible scaling of T such that D and S for probability of error goes to 0 as you scale D and S. So as a function of D and S, you want to figure out T. Okay, the problem formulation, I hope is clear. So here is a very general expression that you can prove, and this is a necessary and sufficient condition. So what we can show is that if the random variables of X, which are your waveforms, and the random variables Y, which are your observations, are independent and identically distributed, then the probability of error, the probability that you will have L errors will go to 0 if and only if the number of samples that you collect T is bigger than L log D over L divided by the mutual information between XS L Y condition given XS L complement. What does all of this mean? Look at the yellow stuff here. That is the true support. Now the true support, supposing I reveal to you the partial green part of the true support. So I tell you what this green part is. So supposing there are 3 non-zero items contributing to your Y, let's say 1, 5, and 6, and I reveal to you 1, which is this green part. Given that I reveal to you this green part, how much this mutual information is simply is asking what is the mutual information between the unknown, which is this red, and the observation Y, given the side information that I have revealed to you. And this is saying that if the number of samples is bigger than L log D choose L divided by this, then you are guaranteed to make sure that you will not make you will make only less than L errors. You will not make more than L errors. And why does this completely make sense? It makes sense because look at the numerator. L log D choose L is like the entropy of in bits if I have revealed to you this part of it, because only this part of it is uncertain, and L log D by L is pretty much equal to the entropy of this part when this part is revealed to you. If you're not clear about this, think about this as D choose log of D choose L. Log of D choose L is the number of ways you can select L things from D things, and that is exactly what the entropy of this expression is. Actually, it has to be D minus this guy choose L, but you know, for making it less messy, I'm writing it this way. What is the denominator? Denominator is the uncertainty reduction per sample given the site information. That is, this is how much uncertainty can I reduce with this channel model is what the denominator tells me. So therefore, this expression is saying nothing but if the number of samples times the uncertainty reduction in bits per sample is bigger than the uncertainty, then I must be able to decode. That's all it is saying. Okay. So that's basically all that is saying. So you can see this in a cleaner way for for probability of error. If the probability that I don't make S errors. Here you can see that this is the number of information bits. That because I don't know anything about the true support, I don't reveal anything to you. And the denominator is the uncertainty reduction per sample. This is the amount of uncertainty reduction that you would get every time you collect a sample. So this expression simply says that the number of samples that you want to collect times the uncertainty reduction per sample has to be bigger than the initial uncertainty in terms of bits that you started. If that is bigger, then you can indeed decode the support. If this is not bigger, then you cannot decode the support. That's because this is a if and only if condition. So the necessity is kind of very easy to see. It's just based on Fano bound. And I'll just try to explain why this Fano bound works out. So imagine I give you a system of different channels, okay, where different amounts of partial support is revealed to you. Here, this amount of partial support is revealed to you, so that also is part of your observations. And then you are given these observations, how much information can I determine about the rest of the system? And then you write down a Shannon Fano bound expression, and you exactly get without this max. Ignore this max and imagine you are in one of those channels. You will get log of D minus this to that. That is exactly the number of bits of uncertainty, and the denominator is exactly the amount of information contained in each sample or uncertainty reduction per sample. And so you can easily prove this theorem using Fano type arguments. Now to come up with an upper bound is a little bit more involved, and it involves something analyzing Gallagher type style error exponents and actually crunching through quite a bit of algebra. So it's kind of hard to point this out in a talk like this, but the papers on this are on the web, so if you would like, I can provide you pointers. Okay. Now, all of this assumes that I had IID observations. But even in the very simple case, you have to deal with non-IID observations. Remember that we were talking about this model y equals x beta plus noise. Now in this situation, what happens is, even though x could be independent identically distributed, y is not independent identically distributed. And the reason is that the beta value destroys the independence of y across the different samples. So in this situation, you can prove a very nice result, and it says that the number of samples has to be bigger than S log D over S divided by the difference between these two mutual information. What are these two mutual informations? The first quantity here is the situation where you would get if you knew beta exactly. And the second quantity here is the price that you will have to pay for not knowing beta. So in general, not knowing beta, the price you have to pay is relatively small because the entropy of beta doesn't scale really with T, but really with S. And so this is like a constant, and what you almost get is S log D over S divided by the mutual information between X's and Y, knowing the values of beta, knowing what the values are, the real values are. Okay, so that's basically what you end up getting even when you have non-IID observation. And this can be extended to the high dimensional setting, and this is the theorem that you can prove. If the support itself grows linearly with dimension, then when is it possible to get S log D over S type result? What is S log D over S? It says that if the support size is S, roughly speaking, the number of samples is also S. You don't have to pay with D is inside the log. You only the number of samples only increases linearly with S. When is this? When can you prove such a result? Even when S grows linearly with dimension, you can prove such a result when the mutual information is strictly bounded away from 0. That's the necessity part, and the mutual information for all possible side informations is also strictly bounded away from 0. So that's your high dimensional setting. Now, why am I saying all of these things? Because once you have proved a mutual information formula, our task now simply is very simple. You can just go and compute mutual information expressions and figure out how many samples that I need in a number of different cases. So coming back to the group testing problem, that's what GT here represents. If I have the noiseless case in the group testing problem, the number of samples, if S of them are defective, is exactly the order of S log square D. What happens if I have some false alarm? Again, just evaluate the mutual information expression, and it falls out that you just have to pay an extra value 1 minus Q. So false alarm here means that if a test is positive with probability Q, you get a negative result, and if a test is negative with probability Q, you get a positive result. If you have such a situation, you just have nothing destroys the linearity of T and S. The number of T, the T still grows linearly with S, but you just have to pay extra in terms of 1 minus Q here in the denominator. This is something you guys may be interested in. What happens if you have a defective or a diluted in the pool? What this means is you may have defective links in your network, and some of these defective links are lossy only with some probability S. They're not always lossy, but with some probability S they are lossy. Then what do you have to pay? How many samples, path samples do I have to collect? The number of path samples is S over 1 minus S squared, where the small s is the probability that you will get a lossy link. Okay, so the main point I want to point out here is that all of these results do not require any elaborate calculation. All that it requires is I have the mutual information expression. I go in, compute this mutual information expression for that particular channel, and lo and behold, I get these results.
I have a question.
Yes.
So that the second result is showing that false alarm probability goes up. The amount of information you need is going down. That seems counterintuitive.
Okay. This expression?
Right. So if Q is not 0, you need less T.
Q is not 0. 1 minus Q. Q is
something less than 1.
Right? 1 minus Q.
It's a required false.
No, maybe I'm misunderstanding you. If one.
So if Q is 0, that means you're perfectly deconstructing everything, right?
Q is 0, there is no noise.
And so at that time, right? So T is small compared to when Q is not 0.
Yeah. So if I have noise, then T is larger, right?
No, normally if you're trying to detect something, you can get away with small amount of information if you're going to allow some false alarms. I don't understand what your Q is here.
Maybe, so you remember the group testing problem?
Yes.
In the beginning?
So you're trying to predict who is the input sets, and sometimes you're going to make errors in decoding probabilities, in decoding who is the culprit.
Right.
No, I'm assuming.
All I'm saying is if there are lots of false alarms, then you have to spend, you have to get more measurements.
Oh, so Q is the errors in measurements.
Q is the errors in measurements. Yeah.
Oh, it's not the decoding probabilities. Yeah, decoding success. Okay.
No, there is no decoding here. I mean, the decoding. So this is algorithm independent bounds. So you can use any algorithm that you want. Q is just a channel flipping probability. The channel flips positive things to negative things and negative things to positive things with probability Q.
Okay.
Does that make sense?
Yes, yes, okay.
And here, S is the probability that a particular link that is lossy does not appear lossy. So supposing there's a link which is not lossy, with probability S, it does not appear lossy. In one of the past measurements, it just so happened it's not lossy. It did not look lossy. So that's what this is. So in this way, you can actually take this mutual information MI as a plug-in formula for many sparse problems. So here I tabulate a large number of different cases: group testing, quantized compressed sensing, sparse matrix, dense matrix. You just compute these different mutual information expressions, and you can just simply tabulate it, and you can come up with your own fancy noise. It doesn't matter. The good news is you can just have to compute a mutual information expression because the numerator is fixed, the denominator is the mutual information. The bad news obviously is mutual information computation is sometimes very hard or impossible, so you may have to come up with bounds, which can be difficult. Okay? So let me move on. Here is a new problem that was recently suggested, and lots and lots of pages were spent trying to figure out bounds for this problem. What is this problem? It's called missing features. So what happens in many statistical problems is I give you y equals x beta plus noise. But then the true x is not revealed to me, meaning the measurement matrix x is not revealed to me because it gets erased. Some components of x get erased with some probability. So with some probability 1 minus rho, I keep the components of x, measurement matrix x, and with some probability rho, I delete it. So zi equals xi with probability 1 minus rho, and zi equals 0 with probability rho. So to analyze this problem, if you sort of do not take the philosophy that we have advocated here, which means that beta has two components, which is the support component, and then it also has a value component, then you pretty much, it becomes a kind of a hard problem to solve, because one of the ways of solving it, a recent paper by Lowe and Wainwright, was to try to impute the values of x by observing z, and then to track it down and try to then estimate beta through that. Instead, our bound is very simple. It just says that the effect of this kind of a thing is simply T miss, which is the missing features, the number of samples that you need with missing features, is equal to the number of samples you would have needed if there were no missing features divided by 1 minus rho, where 1 minus rho is exactly this probability. right? So why can we prove such a result in a straightforward way? The main proof idea is the following. Since we only observe y and z, we also observe there is Markovianity. The probability of y conditioned on z is exactly equal to the probability of y conditioned on zs, where s is the support. Supposing I had revealed to you the support, the Markovianity holds. Probability of y conditioned on zs is exactly equal to the probability of y conditioned on z, which implies we can apply our formula and say the misprobability has to be s log d over s divided by the mutual information between zs and y. And then you can just relate mutual information of zs to y to mutual information between xs to y, and it turns out it's exactly 1 minus rho times the mutual information between xs and y, which implies t over 1 minus rho, because this quantity used to be the sample complexity when there was no missing feature, which means that the features were not erased. Now when the features are erased, you just get t over 1 minus rho. So as you can see, you can kind of think about this problem in quite general context, apply different types of change channels, apply different types of distortions, and try to derive, try to unify a large number of different types of results. So far I have been talking about situations where the coding matrix or the measurement matrix, maybe I should start calling this the measurement matrix X, was independent and identically distributed. But in many cases, it is not independent and identically distributed, it is highly correlated. So what happens if indeed the matrix X, the measurement matrix X is correlated? What cost do you have to pay? And it turns out that the cost you have to pay is this extra expression in the denominator. What is this extra expression? It is exactly the correlation between the measurement matrix corresponding to some wrong support here and the measurement matrix corresponding to the correct support. So if these two are highly correlated, then you need more samples because mutual information is always positive. If they are not correlated, you are back to square one, and you just don't have to, and it's just this mutual information between xs and y. Okay, so we can also extend this result to case where things are going to be very correlated in this manner. So what are some applications of this correlated situation? Imagine the same group testing problem where in the beginning everything was IID, implied that the probability that this first item is in the pool or not in the pool is independent of whether or not other items are in the pool. But now supposing I constrain you to have only m items in each pool, which means pool 1 should contain only 4 people, pool 2 should contain 4 people, and so on. Then immediately you see that it correlates whether or not a second item is in the pool based on whether or not I put the first item in the pool. So in this context, you will, because, or in the network problem, imagine that path length, each path length must contain only k links. In that case, you do not have, whether or not a second link is present or not, is now becomes highly correlated, right? So in that case, you can analyze this and show that at least asymptotically, the restricted case has the same sample complexity as the group testing case. A different situation, which is the correlated Gaussian, if things were not correlated, we get a nice formula which has something to do with log of 1 plus SNR, which means that measurement matrix X is Gaussian, but it is completely independent. Then all you have to pay for is a log of 1 plus SNR, where the SNR is point by measurement SNR. So you take each component, look at the value of x beta, and look at the value of noise. It's the power of x beta divided by the power of noise. So that's the SNR that goes in here.
Sorry.
Yeah.
In the previous slide, asymptotic in what? The matrix size, or the number of samples?
Asymptotic in everything going to infinity, meaning the matrix size is going to infinity, right? Exactly.
Then won't you essentially get kind of independence?
Yes, that's true.
Okay.
But so it's not an entirely satisfactory result because as this matrix becomes larger and larger,
you just pull out some number of
the Bernoulli approaches. The Bernoulli basically approaches. That's what you're pointing out.
Yeah,
that's true.
Can I ask one other question? There is something a little bit different from between group testing and sparse representation, because in sparse representation the sparse basis may not be unique. So there could be two. I mean, if it's over parameterized or something, if there are two different answers, how can you talk of probability of error?
There are two different answers. Come back to this case, right? That's what I'm trying to say. If the basis is such that, so imagine in the sparse representation case, your measurement. So we are dealing with situations where the measurement matrix has is somewhat random. So we are in a random setting. We are not in the setting that it is deterministic. So we are not in a deterministic setting. We are in a random setting. So in this random setting, the only way a non-unique answer can happen is if two different subsets are highly correlated with each other in a noisy situation. And in that situation, you will have to pay for it through this correlation between these different. So think about your over parameterized situation. That's what you're thinking about, right?
Yeah.
So in the over parameterized situation, it could so happen that there may be two subsets of columns that are highly correlated with each other. In which case you will not decode because there is a non-unique answer, and that's exactly what is happening here. Because this is saying this is the mutual information between the observation y and the correct set of columns minus the mutual information between the wrong set of columns and x of s. If x of w is exactly equal to x of s, this is the entropy, and that will be bigger than this guy, and you are going to get a negative answer, which means the sample complexity is infinite in that case.
So earlier in your basic result, when you talked of sparse representation, you had a probabilistic model for the basis vectors?
Probabilistic model for the basis vectors, right.
I see. Okay. For the choice of the basis vectors.
Right.
Okay.
Meaning none of this is, none of these problems are design oriented, meaning you're not designing this thing. It's just that there is a probability distribution that generates these basis vectors. Does that make sense?
Okay, so in that sense it's like random coding in some sense.
In that sense it is random coding in that sense, yes.
Okay.
But you're not coding.
Yeah.
It's just that is what the random variables are. There is an underlying probability distribution with which the basis vectors are generated.
Okay.
So if X is really composed of correlated Gaussians, then all you have to pay for is this extra correlation coefficient C of rho, which means you have log of 1 plus SNR times C of rho, and that C of rho is the correlation coefficient. So for instance, if you want to do compressive sensing with correlated Gaussians, here is a very clean expression you get. What is the normalized sample complexity? What do I mean by this? T divided by S log D over S. What is this quantity? It's roughly equal to 1 over log of 1 minus rho times 1 plus P squared. So this P squared has to do with SNR and the dimension, and that will be true even when you do not have correlated Gaussians but uncorrelated Gaussians. And when you have correlation, what is the extra you have to pay? Exactly this 1 minus rho factor. So the sample complexity is still linear in S, but you have to pay for it with this extra correlation coefficient. And this is how it will look. for different SNRs and for different amounts of as a function of different correlation coefficients. So the x-axis here is higher and higher correlation, and the y-axis here is T of n, which is the normalized value T divided by S log D over S. You can also see that the P here shows that you have 1 over SNR by log D, which also kind of says that unless your signal to noise ratio scales with the log of the dimension, you're not going to be able to recover. Okay? This is another thing that just falls out of this expression. So I have been talking about information theoretic bounds. Let me just put up a slide here which says that you can also do this. Many of these problems, you can solve it and get exactly information theoretic matching expressions using linear programming algorithms. So we have actually shown this for compressive sensing. Here is a way you can also do this for group testing. So in the group testing problem, remember the channel is Boolean. So in order to capture the channel, if you have if you denote by RT the items that are positive, so RT is either 0 or 1, it's either positive or 0. You can try to solve this linear programming problem where you want to minimize the number of positives subject to the positive test. So in other words, since it's Boolean, you want to put a lower bound on the positive set which says that the pool times the items is bounded from below by 1. On the negative test, if there is no noise, then you are saying that every item in this pool is 0, and since the items can only take on values 0 or 1, we can relax it and say Rn is greater than or equal to 0. Same kind of idea also holds for compressive sensing, for quantized compressive sensing, and you can show that you can also actually prove under certain conditions for X that these linear programming type algorithms also recover the information theoretic results. I don't want to get into this too much because that was not the purpose of the talk. I'll be happy to answer questions later. So I don't know what time do I have.
Just carry on. Keep going.
So all right. So I think I have the last few slides left here. I just wanted to provide some extensions to this kind of idea in a totally different setting. There is this idea called value of information. What we have talked so far is the connection between Shannon theory and sparse signal processing. We have shown that it's applicable to many different problems such as linear, nonlinear, quantized, and so on and so forth. There is another idea where what one calls is a value of information. In a control setting, the idea is that you want to pick a sensor or attribute in sensor management problems so that it decreases the uncertainty in your target position, target acceleration, so on and so forth. What many people have suggested is a heuristic, because this value of information to solve it in a general context requires leads to curse of dimensionality. So to overcome this curse of dimensionality, a lot of people have suggested a Shannon theoretic heuristic, which is based on mutual information, and use that to pick the best possible sensor. So what we can try to show is that through this connection from Shannon theory to sparse signal processing, which is an operational connection, we can also then show that Shannon theory is actually more concretely connected to value of information rather than a more heuristic connection. So, for instance, consider the problem of MIMO radar. Here the problem arises which waveforms to transmit. So here are a bunch of transmitters, here are a bunch of receivers. Sparsity here comes in from the following fact that the targets, when you looked in range, speed, and angle space, are sparse in this data cube. So if I look at the range of the target, the speed of the target, and the angle of the target, then it is sparse in this cube, because there are finitely many targets and you only get those finitely many returns. And so if you look at range, speed, and angle, you get sparse returns. So you have a sparsity assumption which says that the number of different alphas such that alpha not equal to 0 is small. So you can think of this problem also as some kind of a problem that we have been discussing, where you have M transmitters and N receivers, you have transmit waveforms and receive waveforms. So what have people suggested in terms of value of information? What they have suggested is somehow thinking about a mutual information between the current estimates for the target. So S is like a random variable, current estimates of the target, and the observation Y. And what you want to do is you have different sets of actions, which means that you can send out different sets of waveforms from your transmitters. What you want to do is maximize this mutual information between S and Y by selecting the best possible wave. The main reason why you want to do this is because you can compute this without actually taking that action. Meaning, without actually sending this waveform, you can compute this quantity and figure out which set of waveforms to send. So how can we make this operational using our ideas? What we have shown so far is there is a tight connection, operational connection between noisy channel coding and sparse estimation. And we also have shown by writing what we wrote so far in probability of error terms that the minus of the log of probability of error is proportional to the wavelength, the waveform length, which is T, times the difference between these mutual information expressions, which is Xs and Y, and the correlation between these different waveforms. So X of S is really a waveform that you would expect to get back if indeed the target was at position S. S tilde is the wrong locations for the target. So we have shown somehow that there is a connection between probability of error and then this difference in this mutual information expression. Now again, like the value of information, we can also actually do all of this without really collecting a measurement. We do not have to actually collect measurements. All it depends on is probability models, bias and likelihood, and computing some entropic quantities. So for instance here, you have unknown target locations, you have a code where the code can shape the waveform that you can send in terms of its power and so on. And if you knew those target locations, you can expect these to be the return waveforms. And then you have a channel where the channel also has reflection coefficients from those targets, and you get an observation. So we can view this sparse problem and optimize what waveforms to transmit in order to best locate the target. And we don't have to actually receive this waveform Y or observation Y or the returns. We can actually do this without doing anything. And that is really tightly connected to the probability of error. That is what we have kind of shown. So that's the kind of extension we have been recently working on to show this. So let me conclude my talk. What we have shown is that sparse reconstruction problem is tightly connected to Shannon's noisy channel coding theorem. The idea is that there are a relevant set of covariates, which is the sparse set. We extract this into a discrete set of possibilities, which we call S. And then the rest of the problem is that the code is really a waveform which the nature codes into excess of T. We view this as a random variable, and the channel produces an output. What we have shown is that it unifies several different problems where the mutual information formula provides precise estimates for sample complexity. Bounds are computable in many cases, and they are tight. We have looked at several different problems, including group testing, linear models, quantized linear models. We can also extend this to Markov group testing and approximate group testing and so on. We have also touched upon this idea of value of information, which is, in other words, something called controlled sensing, and we are working on this. Thank you.